Okay, so when we're starting with a number, remember when we were looking at number systems before how in the number 2015, the 5 represented the ones, the 1 represented how many tens you've got, that was how many hundreds, and the 2 represents how many thousands you've got. So you've got 2 thousands, add 2 lots of 1,000 to 1 lot of 10 and 1 lot of 5, and you get 2015. So that's how a decimal number works. It's very similar with a binary number. Instead of having the numerals 0 to 9, you've only got 2, 0 and 1. So in this number here, we can say it's got 1 lot of 1s, 1 lot of 2s, 0 lots of 4s, and 1 lot of 8s. So we've got 8 plus 0 plus 2 plus 1 equals 11. Okay? So 1, 0, 1, 1 in base 2 is 11 base 10. Now, if you want to convert from decimal to binary, what you need to do, well, there are 2 methods you can do. We'll do the remainder method. What you do, so if we've got 11 decimal rather, so representing like that, what we can do is we can divide it by 2, but we can't have any partial numbers, so we can't have any, like, that'd be 5.5, wouldn't it? So we can't have any of those, so the best way to do it is to have the whole number and a remainder. So if we divide that by 2, we get 5 with a remainder of 1. Okay? So that equals 5 remainder of 1. And so we copy down the 1, your remainder there, and then we're going to copy the 5 is the next thing we're going to divide by 2. So we divide that by 2, and that is going to be 2 remainder 2. Right, 2 remainder 1 rather, sorry. Okay, and so we get another 1 there. And we copy the 2 down to here. 2 divided by 2 is equal to 1 with no remainder. Okay, so there's no remainder. So remainder 0, if you like. Copy that 0 down to there. And now we've got 1 divided by 2. And 1 divided by 2 is 0 remainder 1. Okay? And that 1 becomes, or goes down to that 1 then. So here is our final binary number, 1011. So when we get to 0 here, we stop. So the remainder method is probably the easiest method to do. All you're doing is recursively dividing by 2, and if there is a remainder of 1, then you pop that down on the bottom, and then if there is a remainder of 0, you pop that down. And you keep going, working from right to left in your number. So you're building up your binary number right to left. Okay, so that is one method. The other method, and this one is probably a little bit more difficult, is where rather than having to just keep dividing by 2, you have to kind of remember what all the powers of 2's are. So what are these values here? What are the weights? So the next one will be 16s and so on. So each one of these, this just doubles. Okay? And so what you do is you start with the first one that is smaller than your number. So if we've got 11 decimal there, 11 base 10. Okay? Then the next smallest one, well 16 is too big, so I can't use that. But 8s will fit it. So I'm going to have 1 lot of 8. Then I subtract 8 from this. So 11 minus 8 is equal to 3. Okay? Now the next one is 4. Bigger than that? It is. So I can't have any 4s in it. But in 2's, the next one, 2 will fit in that. So I'm going to subtract 1 of those from that, and I'm left with 1 and 1s. Okay, so I can keep subtracting powers of 2 from it. Okay, and so that works out. It's quicker for me. It takes less space on the board or on my page, but it's a little bit more difficult to do conceptually unless you're really on top of it. Okay, so there are two methods. I don't mind which method you choose to convert from decimal to binary. Okay, so now we've got our binary number. There's something we can think about with octal. So I better explain what octal is first. Octal is like decimal and binary in that it's a number system, but whereas binary has 2 symbols, 0 and 1, decimal has 10 symbols, 0, 1, 2, 3, right through to 9. Octal has, guess how many? 8. Octal, like octopod, octopus, whatever. Octo means 8, so there are 8 symbols in octal. So in octal, the symbols are 0 through to 7. As it's a base 8, and the symbols are 0 through to 7. So 0, 1, 2, 3, 4, 5, 6, and 7. Okay. It's very similar to decimal in that once you get to 7, you clock over back to 0. So 8, the number 8 in octal is, so 8 in base 8 is 1, 0. 8 in base 10 is 1, 0 in base 8. Okay, so you count from 0 up to 7. When you get to 7, that's the maximum number in one digit that you can count. So you increment the next more significant digit up by 1 and then go back to 0 on that one. Okay, so we could try and use that approach in order to count in octal. However, there is another neat method, and it's related to digital electronics because it's actually a octal is a base or a decimal, a number system that is based off digital electronics. If we've got 8, how many? Okay, let's think about the decimal. Decimal, we've got 10 symbols. If I were to count from 0 through to 9, how many binary digits do I need? So if I've got 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. So in decimal, if I went from 0 through to 9, I need 4 bits to represent those numbers. Okay, so remember that, we're going to use that later. If I wanted to get up to 8, so that's 0, 1, 2, 3, 4, 5, 6, 7. So remember in octal, base is 0 through to 7, the numbers are 0 through to 7 rather. How many bits do I need to represent it? Count them off. The 7, 3. I only need 3. I never need more than 3 bits. And if you look at them, I use actually every single combination of 1s and 0s in that. Okay? And if you think about it this way, we've got 8, which is equal to 2 to the power of 3, and the power there, 3, tells you how many bits you need to have that many states. Okay, so 8 is equal to 2 to the power of 3, so with 3 bits, I can represent 8 states, 8 different combinations of 1s and 0s, and therefore I can represent 8 different states with one octal numeral. Okay? So, keeping that in mind, we've got 3 bits here. If I have a binary number, let's say I've got 1, 0, 1, 1, 1, 0, 0, 1. That's my binary number. So let's put another one there. Binary number with 9 bits in it. What I can do is I can group into groups of 3. That group of 3 there, starting from the far right, corresponds with this numeral in octal. So that's 1. This one here, this group of 3 is 7. This group of 3 here is 110 is 6. So this number here in binary equals this number in octal. Very easy to switch between binary and octal. What do you think I would do if I only had, let's say, 5? So if I only had 5 bits, like that, what would I do? Yep.
Just add a 0.
Yep, a leading 0, don't you? So 1 in decimal could be written as 01, or 9 could be written as 09. Doesn't affect the value. Likewise, I could put as many leading zeros as I need to on the binary number to make it a multiple of 3 so that I can use this conversion. So this one, 011, is a 3. Oh, this happens to be 33. Okay, so it is very quick to convert between a binary number and octal. So if I wanted to convert from octal to binary, what do you think I would do? So if I had let's say I've got 56 base 8, how would I convert that to binary now? What do you reckon? So remembering on this side, what we were doing is we were taking a group of 3 binary digits, and that corresponded with a single octal character. Can we do the same?
Yeah, so you have 2 groups of 3.
2 groups of 3. Yep. So this one would correspond with one group of 3, and this one would correspond with another group of 3 bits. So 6 corresponds with 110, so I just write it down. 5 corresponds with 101. And so 56 in octal is 101, 110. Okay? And just to show the...
So that number up there with the 671, what number is that? 671?
671 base 8. So that's what the 8 means, it's in octal. And so this big long binary number here is equal to 671 in base 8. So I converted from binary to octal, or from octal to binary. And it goes both ways, so it doesn't matter. So it's very straightforward. So this is probably the easiest conversion that you'll have to do, and this is the reason why, if you need to convert from decimal to octal, the best way is to convert it from decimal to binary first, and then from binary to octal, because it's really so easy to do that. Then you don't have to. It's not very hard to remember how to do that, and you only have to know how to do decimal anyway. Okay. So octal has 8 separate symbols, 0 through to 7, and to convert from binary to octal or back again, you just groups of 3 binary digits. From the right, you've got to do it from the right. If you do it from the left, you might get it wrong. If you don't have a multiple of 3, just put a leading 0 on your binary number. Okay, hexadecimal is very similar. Hexadecimal though has, instead of 8, it's got 16. So we've got twice as many symbols. Guys, what did I say?
Sorry.
No, I didn't say sorry. I said be quiet.
Good one, Charlie.
Alrighty. Okay, so if I were to continue counting until I'd exhausted every single bit, so we've got 8, 9. If I were to go to 10 decimal, this is my decimal column here, I just keep counting, right? And I'd eventually get down to 1111, which is equal to 15. Okay? I've run out of board space, but you get the idea. I'm just incrementing each by 1, and that corresponds with a decimal value. And so how many separate states do I have before I've exhausted every possible combination of 4-bit binary? So what would I have? How many would I have there from 0 right through to 15? 16, isn't it? So it's 15 plus a 0, so that's where the extra 1 comes from. Alright, so I've got 16 different states that I could represent that, and hexadecimal is base 16. And it's no coincidence that it's base 16, because it is also a digital number system. Okay, so there are 16 states, and we're obviously going to run out of numbers. If I go to 10, well, don't write 10 because I want to represent everything with a single character. So what I need to do is I write it from 0 through to 9 as per usual. But when I get to 10, I start with A. And I have to stop at F because F corresponds with 15. And once I've done that, that's it. So I've got my 16 states, 0 through to 9, A through to F. So A would be 10, B would be 11, C would be 12, and so on. Okay, now remember what we did with Octal. When if I had the binary string 010, that corresponded with 2 in Octal. If I have the binary string 1001, that corresponds with, well, I can't represent that in Octal with a single character because I've only got 3 bits with Octal. Now I've got 4 bits, but in hexadecimal or decimal I can represent with a single character as 9. If I've got 10, now the only way I can represent the value of 10 in a single character is using hexadecimal. So hexadecimal has 4 bits available to me, and it's got up to 15 different, well, it's got 16 different states. So state number 10 would be 1010. Okay, so again, like we did with the octal conversion, we're looking at groups of 3 with octal, groups of 4 with hexadecimal. So if I have this string there, so this string of 8 binary digits, all I need to do to convert that into hexadecimal is by grouping the groups of 4. So 1110 corresponds with, well, I don't have it there, but it's actually 14. So it's 14 base 10, but 14 is actually E in base 16. Okay, so 1110 corresponds with E in hexadecimal. 1011 is 11 in hexadecimal. 11 in decimal, sorry. So in 10, which is equal to B in base 16. Okay? And this is actually how I do it. I just remember that A is the first one that's after the 0 to 9, and that must be 10. So you can sort of work it out from that. And so if I have B is the second one, that must be an 11. So this number here is equal to BE in base 16. Okay? So that is actually a number in hexadecimal. So this 8-bit binary string corresponds with BE base 16. Likewise, I can do the same sort of thing. I can have 7A in hexadecimal, and I can work out what it corresponds with as far as a binary string. So that would A is equal to 1010. Okay, and 7 equals 0111. So all I'm doing here is writing binary digits that represent A in hexadecimal, and then before that the binary digits that represent 7 in hexadecimal. Okay, so I can convert from hexadecimal to binary or binary to hexadecimal in a very, very similar way that we did with octal. Octal was groups of 3, hexadecimal was groups of 4. Okay, so remembering 16 is is equal to 2 to the power of 4, so that's how many bits I need. Okay, now finally, the other number system that we use in electronics is something called binary coded decimal. Now this one's important because you need it when you are using digital counters, decimal counters. So, binary coded decimal is very much like hexadecimal in that it's a digital number system, and where 0000 in base 2 is equal to 0 in base 10. Okay? And it's a decimal system in that there are 10 states, but we're representing it as a binary string. So 1 would be represented by 0001 base 10. Okay? And we're representing it with 4 bits here, even the ones that we don't need to. So I could represent these two numbers with just 1 bit if I really wanted to. But with binary coded decimal, we need to represent it with 4 because we're showing that, okay, if I had the digital number 23, so if I wanted to display that, what I need to do is find the binary coded string that represents the 2 and the binary coded string that represents the 3, and then concatenate them together. And if they're not the right length, so if I just make the 2 1 0 and the 3 1 1, well, it's only 4 bits. That doesn't represent a binary coded decimal that is for 2 decimal numbers. So what I need to do is, well, I can populate this whole list. It's 2 base 10 and so on, right up until I get to 9 1 0 0 1. And anything after this is actually an illegal value. It doesn't actually make any sense. So 1010 is not a binary coded decimal value because I'm actually out of digits. I've got my 0 through to 9, and that would correspond with 10, wouldn't it? And 10 is, in decimal, I need 2 digits, don't I? Okay? So these are the binary coded decimals codes. Okay? So we're basically, all we're doing is we're taking the numeral from our number and encoding it as a 4-bit binary number. So in my 23 example, well, let's do 35. In decimal, the 5 is 0101, and the 3 is 0011. And so that would be the binary coded decimal for 35. Okay? So when I have a circuit that might have a 7-segment display on it, and I input this binary coded decimal input on it, because it's a digital circuit, it needs a binary coded decimal circuit input, and this one, and I had them set up right, it would display 35. Okay? So any binary coded decimal symbol I can create a value from in the same way. Now it would have to be a multiple of 4 for it to actually be a binary coded decimal. You can't have a 7-bit binary coded decimal value because that makes no sense. You must be a multiple of 4 for it to make sense. So if I had this number, okay, so if that was my binary coded decimal value, then I need to convert it by grouping it groups of 4. That one corresponds with 5. That one corresponds with 8. Okay, so I can convert from one to the other reasonably easily. All I need to do is remember how to convert between binary and decimal from the numbers 0 to 9. That's all you need to do. Okay? And after a while you get to remember how to do that. So I can do these in my head because I actually do that second method from binary to decimal conversion. I count how many 8s I've got, and then how many 4s I've got, how many 2s I've got, and that sort of stuff. Alright. You learn lots, Chris? Good. Alright, anybody got any questions before I finish up?
Do you add subscript BCD at the end when you're writing?
Yes, you should always add the subscript because that is very different than that number in binary. So that number in binary will equal something very different than that number in BCD. So if I type that out and work out its value in binary, it's certainly not going to be 85 because I've got this one up here, which is something like 200. That's got a value like 512 or something, or 256. So it's going to be a number bigger than 256. So it's clearly not the same. Okay? And if I had a 3-bit binary coded decimal, a 3-digit binary coded decimal value, so like 185, then I would have 12 bits, and one of those is going to be very, very different than the binary equivalent. Right? So you must state what the base that you're using.
BCD binary coded.
Binary coded decimal. I'll write that down. So binary. BCD, it represents each decimal numeral with a 4-bit binary number. So that's the important thing. It's got to be 4 bits, and each numeral in your decimal. So if I had 2015, the 2 would be represented by a 4-bit number, 4-bit decimal binary number. The 0 would be represented by another 4 bits, the 1 by another 4 bits, and the 5 by another 4 bits. So I'd have a 16-bit binary string there. That would be my binary coded decimal for a. Now it's not particularly efficient because I have a whole bunch of illegal states that aren't being used. Got 6 of them, in fact. However, it is required that you use 4 bits because 3 can only get you up to 7. I need the 8 and the 9 to be gained by these other 2 bits here, this other bit. Okay, and in order for it to actually represent a binary coded decimal number, it has to be groups of 4. Otherwise, you lose place value for each one. All right. Anybody got any questions about it? Excellent. I'll put that up on the YouTube channel.